Congratulations, you've made it through Model 2 and you're getting prepared for your second exam. This is the distribution part of the class. Generally, it's a little bit more difficult than the first part of the class because the level of difficulty on the topics has kind of increased. So what I want to do in this video is kind of walk you through the topics that we covered, talk a little bit about them and what you're responsible for and sometimes what you're not responsible for, and then show you some of the resources I have available to you. So first things first, we talked about random variables. We were moving from our probability and we were talking about events and outcomes and probability, and we moved into random variables. A random variable is just a variable that gives a number to an outcome of an experiment. And so the random variable assigns a number. The type of number that it assigns can be defined either as discrete, where the numbers jump from one value to the next, like 0 or 1 or 2 or 3, or continuous, where there is no jumping. The amount of time it takes me to drive from home to USF is a continuous random variable because it doesn't jump from 24 minutes to 25 minutes. It could take me 24 and a half or 24.2 minutes and anywhere in between. So there's two different types of random variables. The probability distribution part comes into play when we start assigning probabilities to the various outcomes of the random variable. And we saw there were two rules that always need to be true with probability distributions. First, probabilities have to be between the values 0 and 1. And second, when you sum up all those different probabilities for all the different values that the random variable can be, they have to sum to 1. You should be able to differentiate between the discrete and the continuous. And as we saw in this module, that the type of variable kind of points us in a direction of different distributions that we can take a look at. The binomial distribution was a good example of a discrete random variable. There are others, but that's the one that you're responsible for. The normal distribution is our most probably popular or most common distribution, and that works for continuous distributions. When you're working with discrete distributions, there were some formulas for finding means and variances and standard deviations. You only have to worry about the mean. You should be able to find the mean of a discrete random variable. We took a look at this, and it's where you get the probability distribution. Think about it usually in a table where you have values of x and the corresponding probabilities. You take the value of x and multiply by the probabilities and sum them up, and that gives you the expected value. The expected value really represents an average. And a couple different ways of symbols you can use, a couple different ways of writing it. You can do the expected value of x, you can do mu, which is a population mean. The first discrete distribution, actually the only discrete distribution that we spent time with, was the binomial. You should be able to work binomial distributions really, really well. You should first be able to identify when you have a binomial. Sometimes these are called the 4 criteria or the 4 conditions. You should know them, and you should be able to identify when we're working with a binomial or when we're not. The binomial has a collection of n experimental units, or a sample of n experimental units. There's 2 outcomes, success and failure, for those experimental units. The probability of success is p. The probability of a failure is 1 minus p. And those experimental units, or trials as they're sometimes called, have to be independent of one another. When those 4 conditions are met, you have a binomial. And one of the reasons we like when we have binomials or any of these distributions is because there are some straightforward methods of calculating probabilities. So you should first be able to identify when you have a binomial, and then you should be able to solve probabilities using a table. And I showed you the cumulative binomial tables, but I also want to mention you should be able to solve, or you can solve those using the binomial.dist distribution function. And I showed you how to do that, and I also required that of you on the project. In our exam settings, where you have the ability to be online, you can use Excel, you can use the tables, but you need to work with solving binomials. Working in the tables and that binomial distribution function work really well with less than or equal to probabilities. They're called cumulative probabilities. So you should be able to work your magic with those. When you're working with binomials, means and standard deviations are really straightforward. The mean is just n times p. The standard deviation is the square root of n times p times q. And so calculating means and standard deviations of binomials is something you should be able to do quickly and easily. Calculating means of other discrete distributions, use that formula that I just mentioned. Again, calculating variances or standard deviations of other discrete distributions you're not responsible for. Turning to our continuous distributions, we have the normal. Binomials are characterized or described by values of n and p. Normals, you need a value of the mean and a value of the standard deviation. So the symbols we typically use are mu and sigma. I introduced you to z distributions and showed you how to use a cumulative normal table. But mainly your normal work is going to come through other distributions. The z distribution has a mean of 0 and a standard deviation of 1, and there's a table that we took a look at, and I walked you through how to work with that. But really, it's the other normal distributions. You should be able to work with a mean of mu and a standard deviation of sigma. And these could be any value. Sigma has to be a positive value, but really there's infinitely many combinations of mu and sigma. You can solve all those normal distributions by changing them into standard normals. But really the best or the easiest way is to use the functions that we looked at in Excel. And I am not an overly huge Excel fan. I love Excel for a lot of what it does. I have a love-hate relationship with it when it comes to statistical analyses. It does some things really well, other things it does not. But boy, does it make working with normal distributions a lot easier. It allows you to use normal curves that have any value of the mean, any value of the standard deviation. And you get cumulative probabilities for the normal distribution as well. There's a normal.dist, the distribution function, and then there's an inverse function where you give it a cumulative probability and it'll tell you the value that you're looking for. And you use both those functions, or should have used both those functions on your second project. So working with normals, working with binomials and normals is key to success this semester. The binomial distribution we won't see much after Module 2. The normal distribution is going to be sticking with you, and we're going to see that in Module 3 and Module 4 as well. But we also see it when we talk about sampling distributions, right? Which I'll get to in a second. The last topic with normals is I gave you several different techniques for assessing normality. On the project, I had you take a look at 2 of the techniques that you wanted to take a look at. On the exam, all you have to do is answer questions. So you don't have to be creating anything, but you should be able to identify. If I gave you a normal probability plot, for instance, or if I explained what the IQR over S was, if when I do the work, I want you to do the assessment. And I got to make it pretty easy. I can't give you a distribution that's kind of sort of normal. It's got to either be very, very normal or very not normal. So, but you should be aware of those 4 techniques for assessing normality. The last topic that we covered in this module is sampling distributions. Sampling distributions are interesting. You take a sample, you calculate a value of a statistic like a sample mean, for instance, or a sample proportion, and then you do it again. You take another sample, calculate another value of that statistic, and then you do it again and again and again, and you pile those things up on a number line. That's called the sampling distribution. You should have a general understanding of what a sampling distribution is, but really that most of the questions will come from the sampling distribution of X bar. That's the one we really dialed into and took a look at. And I showed you when you're working with sampling distributions of X bar, there's 3 things that we typically need to know. We need to know what the mean is. And fortunately for us, a sampling distribution of X bar, the mean of the sampling distribution is equal to the population mean. We also need to know the standard deviation, and this is where it gets a little different. When you're working with X's, when you're working with individual observations like the normal distribution, the value of the standard deviation is sigma. When you're working with X bars, where you're taking a sample of N, looking at a whole bunch of different X's and averaging them, then the standard deviation of the sampling distribution of X bar, it's not just sigma, it's sigma over the square root of N. And we saw a couple different ways to get to normal sampling distributions. One is, if we're starting with a normal population, the sampling distribution will also be normal. But the one that we typically have to use is the central limit theorem. And that's if we take any size, if it's a large size, I shouldn't say any size, as long as it meets a criteria large enough sample, then the sampling distribution of X bar is going to be approximately normal regardless of the shape of the population. And the rule of thumb we use, and the sample size rule of thumb has changed from one area of statistics to the next. When you're working with a sampling distribution of X bar, a large sample is considered to be 30 or more. So as long as you take 30 or more, we have a large sample, the sampling distribution of X bar will be approximately normal. That's what the central limit theorem guarantees. The mean of the X bars is mu. The standard deviation of the X bars is sigma over the square root of N. And the last thing you had to do is work with some probabilities. And you saw an example of this in your project. Find the probability that the sampling distribution of X bar produces an X bar value that's bigger than this number, that's less than that number, that's between these 2 numbers. And really the way you solve the sampling distribution of X bar problems, the probability problems, is exactly the same way we solve the probability problems with the normal distribution. Okay, the normal.dist function can be used for both normals and also sampling distribution of X bar. We typically don't use the inverse function when you're working with sampling distributions. I could probably contrive a problem, but it's not the typical problem. So working with the norm.dist. The big difference is you're putting in a different value for the standard deviation. When you're working with the x's, when you're working with individual observations, you put in a value sigma. When you're working with the x bars, you put in a value sigma over the square root of n. You are going to get very thoroughly tested on all that. If you want a practice exam, Module 2 sample exam is sitting right there. I have, I think, I don't know, I think 16 questions, I don't remember. But you don't see any, well, in this video, you don't see any answer videos, but when you're looking at this, you will, because that's part of what I'm doing before the semester. I'm going through and creating some answer videos for the practice exam. So by the time you're here, in addition to having the sample exam posted, there will be 2 answer videos. Again, I'm going to encourage you to prepare for the exam. Take a look at the examples I'm going over in class. Take a look at your competency checks. Take a look at your project. Take a look at the sample exam. Take a look at the homework problems from the chapter in the text. Those are all really good questions to prepare for. Don't watch me answer the sample exam. I'm going to do really well. You answer the sample exam and then use my resources when you run into trouble. When you have questions, you know how to get hold of me and the teaching assistants, and good luck. So long.